Welcome Math 107 students to the demo for lesson number 7. Lesson number 7 involves finding solutions to absolute value equations, polynomial equations, and a special polynomial equation called quadratic equations. Today we're looking at just quadratic equations that have real solutions, real numbers for their solutions. So let's take a look at the first demo here, the first exercise, equations involving absolute value. We found two solutions, x equals 4 and x equals -4, to the absolute value equation, the absolute value of x is equal to 4, in the preview exercise number 1 above. We can check these solutions since we know that both 4 and -4 lie the same distance, which is 4 units from 0 on the number line. Visually, we can find the solution to this equation by graphing a horizontal line. So you let this part of your equation be the horizontal line, y1 equals 4, and that's right here, y1 equals 4, it's a horizontal line. And then you let the left side of your equation be y2, and so y2 equals the absolute value of x, is this equation right here, this V-shaped equation. Oops. Let's see if I can do a little bit better there. And to find the solution to this equation, we see where these two graphs intersect. What values do they have in common? And it should be no surprise to you that both of these equations have x equal 4 and x equal -4 as a solution. If you looked at the points that correspond to x equal -4 and 4, so here's x equals -4. When you take the absolute value, it's 4. And here's x equals 4, and the absolute value is 4. So notice both y values are 4, which correspond to this equation, the horizontal line. And they also represent solutions to this absolute value equation. Okay, so in general, if we wanted to take this result and think about how do we solve any absolute value equation? When you solve any absolute value equation, you'll always have some type of algebraic expression in between those absolute value symbols. And you'll have some constant number here. So to solve this expression, just like we did with this very simple absolute value equation, we let x be 4 and we let x be the opposite of 4. So similarly here, whenever you have an absolute value equation, you're going to let that algebraic expression that's inside, you're going to set it equal to c, whatever value c is, and then at the same time you're going to take that algebraic expression and you're going to set it equal to the opposite of c. So remember, when you're solving an absolute value equation, you begin by taking these two branches, these two lines, and you set up two equations similar to the one that you see here. So let's take a look at an example. So before we get involved in all the algebra of solving an absolute value equation, let's take a sneak preview of the solutions to this absolute value equation. Graphically, we'll see if we can find the solutions to this. So this absolute value equation says, take the absolute value of this expression, 2x minus 3, notice I put it in parentheses, and whatever x is, you want the value of x that when you put it into this expression and you take its absolute value, it would equal 7. Okay, so what does that mean on the graph? Well, you're going to set up your horizontal line, y1 equals 7. And then you're going to graph the absolute value of 2x minus 3, which looks like this blue graph. I did these graphs on GeoGebra. So it's a free software package that you can choose anytime you want to look at things in class. And where these two intersect is the solution to our equation. So let's see what are the solutions here. X equals -2 and x equals 5. So notice before you even begin this process, realize that the absolute value of any expression will always have this V shape, and the constant will always be a horizontal line. So you'll always have two solutions. That's the key. A lot of students do absolute value equations and they just come up with one answer. But anytime you cross, except for when this absolute value equals 0, right down here, you're only going to have one solution. But anytime you cross this absolute value graph with a horizontal line, it's going to intersect in two places. So the two graphs intersect at -2 and 5. Therefore, the absolute value equation, 2x minus 3 equals 7, has two solutions. So let's take a look at how we would arrive at these answers algebraically. We don't always want to be drawing graphs to find these answers. We know that the expression inside the absolute value bars, and that should be 2x minus 3, not 3x minus 2, must equal both +7 and -7. So to solve this absolute value equation, 2x minus 3 equals 7, we create two equations without the absolute value bar. So you take this expression and you set it equal to 7 for one of your equations, and you set it equal to -7 for the other. And look, you have two beautifully simple linear equations to solve. So you add 3 to both sides, and you get 2x equals 10. And then you divide both sides by 2, and you get x equals 5. And now you add 3 to both sides in your second equation, and you get 2x equals -4. You divide both sides by 2, and you get x equals -2. And you can see that these are exactly the same solutions we got through the graph. So if you have any doubt, remember you can always go back and put in the value for x that you found and check it. Does this equal 7? Here's your check. The absolute value of 10 take away 3, does that equal 7? The absolute value of 7 equals 7. You're a happy camper. Now try the next one. Is the absolute value of 2 times -2 minus 3 equal to 7? That's the question. -4 minus 3, does that equal 7? The absolute value of -4 minus 3, the absolute value of -7 equals 7. That's true. So you know you've done this correctly. Okay. So basically, all you're doing is you're saying, I know what can live inside of this absolute value symbol if the absolute value is 7. What can live in here is either a 7 or a -7. So you take whatever is inside the absolute value and you set it equal to 7 and -7, and you've successfully solved an absolute value problem. Okay. So what happens when we have absolute value equations when there's a lot going on around the absolute value? Notice this equation, we've already isolated the absolute value equation. There's nothing being added or subtracted to it. There's nothing multiplying it. So when you see something like this, your goal is to get whatever's in the absolute value all by itself. We call that isolate. Isolate the absolute value. Okay, some students make the mistake of thinking of this like the distributive property, and they distribute the 3 first through the absolute value. Just imagine the absolute value symbols as like a barrier that you cannot get into. And the only way you can release that absolute value symbol is when you set the expression equal to the constant that's on the right hand side, when there's nothing else around the absolute value. So if this were a linear equation that you were solving, you would first add 5 to both sides, and then you would have 3 times the absolute value, 2x minus 1. I like to put my expressions inside the absolute value in parentheses. And I'm going to make the absolute value a different color, just so we remember that we're not dealing with parentheses here. Now again, I can't break free from those bars here until nothing else is on that side. So now I have to divide both sides by 3. And now I have the absolute value of 2x minus 1 equals 7. Now I have my expression on the left-hand side. I'm taking the absolute value of an expression. It's been isolated. There's nothing multiplying this absolute value. There's nothing being added or subtracted. So this is where I make my 2 equations. I take my 2 little branches and I say, okay, 2x minus 1 could represent a 7, or 2x minus 1 could represent a negative 7. And now it's a very easy process for Math 107 students once they get this far to solve these equations. So these are the 2 solutions, and you could check them on your own time, okay? So absolute value equations, why do we even think about these or put this into this section? And it has to do with a strategy we're going to use for solving certain quadratic equations, which will be coming up next. So now we're going to take a look at quadratic equations with real number solutions. So what are quadratic equations? Quadratic equations are what we call second degree polynomial equations. That means if you look across your equation from left to right or right to left, the highest power you will see is a 2. So both of these equations are considered quadratic. Notice they look a little different, but in the end, if you squared this x minus 7 and then multiplied everything by negative 2, you would have an equation that would look very similar to this. So the key here is seeing that 2 is your highest value for your exponent. We call that the degree of the equation. So another way to say this is second degree. That's what this means. Okay? So in general, the quadratic equation, if we put all of our information for our equation on one side and have 0 on the other, we call this the general quadratic equation. Your book calls it the general quadratic equation. Sometimes people call it the quadratic equation in standard form. This is just another term, standard form, for an equation that looks like this. Now, a cannot be 0 here, because if it was 0, then this would disappear and we would just have a linear equation. So a, b, and c are real numbers. They could be nice integers like 2 and 10 and negative 3. They could be fractions. They could be irrational numbers like square root of 5. But a, b, and c are real numbers. So we're already familiar with techniques used to solve linear equations. So let's see what type of methods and strategies we can use to solve quadratic equations. There are 3 general strategies you can use, but a lot depends on the form of the original quadratic equation. Sometimes factoring can be very quick and easy to use to solve your problem, your quadratic equation. If you have a quadratic equation that has a certain form, like something square equals a constant, then this idea of the square root property can be used quickly. But when all else fails, your quadratic formula you can use on can be used to solve any quadratic equation. So you might say, why would I even bother with factoring or this square root property? Sometimes a quadratic formula can be sort of cumbersome to do and a little tedious for students, and there's opportunities for you to make little like arithmetic errors. So if at all possible, some of these other methods, it's just nice to have them in your toolbox for flexibility with your problem solving. It's always nice to have more than one method. So let's take a look at some quadratic equations. So here's a situation where we're going to be looking at solving quadratic equations by factoring. Why do we factor? Because we have this beautiful property of multiplication where we say, if I have two quantities that I'm multiplying and they equal 0, then I know something about these factors, A and B. If they equal 0, then either A is 0 or B is 0. So in words, this zero product property says if the product of two numbers or quantity is 0, then at least one of the numbers or quantities is 0. So this is an idea we use in solving problems other than quadratic, which you'll see in a little bit when we get to polynomial equations. And it's a strategy that we use throughout the remainder of the course. So let's start with this first quadratic equation. Now notice, to solve a quadratic equation, in order to factor it, to use this property, you must have 0 on the right-hand side. I could factor x squared minus 12x, but I would be here all day trying to figure out what values x must be to equal negative 27. So the first thing we're going to do when you see a quadratic equation is to put it in what your book calls the general form, and I call standard form. That means you get all your non-zero terms on one side and you have 0 on the other. So let's use a little bit of language here. This first term, any term in your quadratic equation that has 2 as the exponent is referred to as the quadratic term. The next term, the negative 12x, because the exponent on the x is 1, is referred to as the linear term. And last but not least, the constant, in this case 27, is called the constant term. So I have all three terms on the left side of my equation and 0 on the right. Now, it doesn't mean you always have 0 on the right. You might have 0 on the left. It doesn't matter which side 0 is on. What's key is that you have a 0. So to make this problem useful for us for solving for x, you want to take this addition and subtraction problem and you want to turn it into a multiplication problem that equals 0. So this is one where you'd want to factor. You're looking for factors of 27. Take your constant term, factors of 27 that add up to 12. So the factors of 27 that add up to 12 are 9 and 3. So I set up my two parentheses, set it equal to 0 because I'm solving an equation with another equivalent equation. And I have x and x, 9 and 3, subtraction, subtraction. So now you can look at this and say, hey, this is going to be 0 if this factor is 0, so you set that equal to 0, or when this factor is equal to 0. And you can see it's one step from here to get to your two solutions, 9 and 3. So the solutions to this quadratic equation are 3 and 9. You put them into your solution set, or you circle these, and of course that's after you check it. Okay, don't forget to check. All right, so note that this is an important statement here because it's in bold font, that factoring one side of the equation is only going to help you when you have a 0 on the other side. That's the only way you can use this property. So I wanted to show you how you could visually solve this equation two ways. The first way is to actually set up a graph similar to what we did in the first case up above with the absolute value. I'm going to let this constant, negative 27, be this horizontal line right here. And then I'm going to let x squared minus 12x be this parabola that you see right here. I'll outline in blue. And where those two intersect, that represents the solution to your equation, 3 and 9. So that's if I graphed x squared minus 12x equals negative 27. Again, this was y set equal to y1, and this was set equal to y2. So when you have this U-shaped graph and you cross it with a horizontal line, except at this one point right there, with exception to that one point, which we call the vertex, you will cross in two spots. You have two answers. Okay, so you might be wondering, what is this graph on the right? Well, notice we said that this equation, x squared minus 12x equals negative 27, was exactly the same as this equation, x squared minus 12x plus 27 equals 0. So if we were to graph y equals x squared minus 12x plus 27, we would get this parabola. And the value of y that we are interested in solving for is letting y equal 0. So when you solve a quadratic equation, you're finding the values of x that make y 0. Well, guess what? That's your x-intercepts. And you can see here, 3, 0, and 9, 0 are your solutions. So x equals 3 and x equal 9 visually are your solutions. So regardless of which of these equations you graph, you'll see that you have the same exact answer. Okay, so remembering here that we have two solutions to the quadratic equation so far, and this is important to remember, particularly when you're using the next strategy for solving quadratic equations, and that's called the square root property. So when do we want to use the square root property? The square root property is very useful when you have your quadratic equation and the linear term is 0. So you'll end up with a quadratic equation that has this form. Or it may start out looking like this. C or negative C on the other side. Okay, so at your seats, I'd like you to take a few minutes to solve this quadratic equation right here. And I do want you to spend some time before you put the video back on thinking about this equation. Okay, so hopefully you've had an opportunity to try to solve this equation. So notice you have no x term here. So b in this case equals 0. So this is where the square root property is important to use, or easier to use than, say, the quadratic formula. But I also want to mention to you that even in this situation, you can factor. So I'm actually going to show you both approaches. I know the topic is the square root property, but I just want you not to be so avoidant of factoring, because it's a very useful skill to have. Okay. So first, let's talk about factoring. So remember, the whole key of factoring is that you wanted to have 0 on one side and a multiplication problem on the other. So the first thing I'm going to do here is I'm going to subtract 27 from both sides of the equation. Now at this point you have two choices. You notice that 3 is the greatest common factor. So you could divide both sides by 3 and get x squared minus 9 equals 0. Or you could just factor the 3 out of 3x squared minus 27 and get x squared minus 9 equals 0. Either way, 3 will never be a factor that could ever equal 0. So it's not part of your solution in any way. So that's why sometimes we just divide both sides by 3 and we wind up with x squared minus 9. Now we know that x squared minus 9 is the difference between two perfect squares, and oh, are these easy to factor. Okay, and you can see here you have two solutions, plus and minus 3. All right, so that's factoring. Maybe I'm starting to convince you that factoring is kind of a fun and easy way to solve some of these quadratic equations. What about the square root property? Okay, so the square root property, we want to get the form, we want to get it to look like this. X squared or anything square equals some constant. Okay, equals some constant, C. So we have 3x squared equals 27. So in order to get x squared, I have to divide both sides by 3. X squared equals 9. And now I find, or I take the square root of both sides. And remember, this square root asks for the positive square root only. So when I now use this symbol, the answer to the square root of x squared we discussed in our preview exercises is the absolute value of x. And the answer to the square root of 9 is 3. So we now know that the absolute value of x equals 3 has two solutions, 3 and negative 3. Okay, and again, this corresponds to what we know about visualizing this type of quadratic equation. If you had a little graph of these two, x squared would look like this, and y equal 9 would cut across, and that would happen at negative 3 and 3. So what's really important here is that you avoid the common mistake of saying x squared is 9 and just solving this for the positive value of x only. Okay? So by introducing you to this idea that the square root of x squared is the absolute value of x, you now know how to solve absolute values equations. You know that absolute value equations have two answers. If left to your own devices, you would probably end up only getting one solution unless you've done a lot of these problems. And this step right here that I've dotted with the arrow has been a step left out in most of your math education classes before. So it might feel a little strange, but it will guarantee that you get both solutions, as does factoring. Okay, let's take a look at what's next. As you can see from the previous example, using the square root property sometimes can cause you to forget there are two solutions. Why? Because we forget that the absolute value of x squared, again, it's asking for the positive absolute value, must be represented by the absolute value of x, whatever your base is. And then solving the absolute value equation has two solutions, except for when the absolute value of x is 0. So in general, we can make a statement about a quadratic equation that has this form. If c is a non-zero real number, then the solutions to this quadratic equation is u equals the square root of c, the positive square root of c, or u equals the negative square root of c. So when you see a quadratic equation that has this form, then u is equal to plus or minus the square root of c. That's the end result. So if you're capable of just going from this step to this step, and you understand how you can get here, and that's critical, is understanding why there's a lot left out in between here. But if you understand the process of why you end up with both a positive and a negative square root, then it would probably be easier for you to remember how to go from this step to the final step. But if you're still a little leery of how you get there, it's probably really important that you try to go through the steps using the absolute value that we did in the previous example. Okay, so let's solve a quadratic equation using the quadratic formula. So the quadratic formula can be used to solve all quadratic equations, and the formula is derived from the general quadratic equation by using an algebraic method called completing the square. So in other words, just like we go through a series of steps when we solve an equation to get down to x equals something here, there's a whole series of steps. The same is true for the quadratic formula. We can solve this equation with a, b's, and c's for x with the result x equals being all in terms of a, b, and c, using this method called completing the square. Now, we won't be going through that in class, but it's actually an interesting exercise for you to read in your book or online to see how you can get from this equation down to this equation. So I usually have my classes sing the quadratic equation, but given that I haven't had my first cup of coffee yet, I think I won't sing. Will I sing or won't I sing? All right, x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. It's to the melody of Ring Around the Rosie. All right, so this is the quadratic formula. And so if we were going to use the quadratic formula, remember that the original equation was always set equal to 0 in order to arrive at the solution.